All right, so welcome to the end of week 2 here. You guys just took your first quiz, so I guess you can say you're officially doing statistics now that you've turned something in. But we're going to continue our discussion today talking about picking up where we left off, basically. Just to remind you, we were talking about ways of organizing and showing data, and we were kind of in the middle of the quantitative, the stuff with numbers, right? And so we'd seen a couple different ways of dealing with qualitative, and then the similar ones with quantitative. And then with quantitative, we spent some time looking at box and whisker. I'm going to show you another one called stem and leaf. And then we'll keep moving on talking about data and some of the other things that we look at. But before we do that, I want to address some homework questions. I had a couple of people ask me before class to go over a couple things. So I've put on my list to talk about lower class boundary. And at least I think I know what that is pertaining to. And then also cumulative relative frequency. So we can definitely talk about that as well. Are there any other topics you want me to add to the list of things to review homework wise or other? You can go ahead and throw it in the chat or yell it out at me.
Wait, Bruce, I had a question. Real, just like kind of relating the homework topic.
Sure.
You want us to just ask questions like during lecture, like right now, or would it be better to like email you or come to office hours? Like what? Like if we have questions like off, like on like a Friday or Saturday.
Yep. Okay. So the answer to your question is yes. Like you can come to me in any of those ways. We can talk about them in class for sure. You can find me during office hours if you just want to talk one-on-one with me. If it's a day where we don't have class or an office hour, like you just mentioned, like a Friday or a weekend, you can definitely send me a message either through Canvas or an email. And just realize it might take me a while to get back to you if it's a weekend. But any of those are fine, and I will respond to them and help you out in any way possible. So basically, however you want to get it to me, get it to me.
Okay, thank you.
But I always reserve a little bit of time at the beginning of class, at least in my planning in my mind, to go over things. And so I will always at the start, like today, say, hey, are there things you want to talk about? And so that's a really good time if there's something in particular you want to look at that we can do. So I see while I was talking here, responding to that question, Carolina just put in the chat, she asked if we can go over what intervals are in box plots. We can definitely talk about, I'll do a little review of box plots, box whisker plots in general. So I'll put that on my list as well. All right, anything else?
My quiz, I had trouble downloading and typing on it, so I just like wrote it. Is that okay? Like with
totally.
the actual draw tool.
As long as it's legible for me to read, that's totally fine.
Okay. I tried. I'm pretty bad at drawing on the mouse.
Yeah, I am as well. That's the only reason why I said that. That's totally fine. Another option just for the future is you can literally write them down on a separate piece of paper, write down your answers, and then take a picture of it or whatever. You know what I mean? So like you're reading it off of the screen, but then you're writing down, okay, so this one asks for, the mean is 14, the median is 38, whatever.
Okay, thank you.
Yeah, you're welcome. All right, well, let me go ahead and share a whiteboard here then on the computer, and let me address some of those questions that people had. I'm actually going to start with the box and whisker plot because that was the most recent thing, and I just kind of want to remind you how these work, right? So we call this a box whisker plot. And for these, there's always a box with a value designated somewhere inside the box. And then there are whiskers. Now, I'm just going to tell you that I have a habit of putting vertical lines on my whiskers just to help reinforce that those are the ends. They don't necessarily need to be there, but you'll see me do that. So I often think this looks like a TIE fighter. We've already established I'm a bit of a Star Wars nerd, so we're good there. Okay, so in terms of what all of goes into this box and whisker plot. There are 5 numbers that matter. All right, there's this where we've got the dashed line that's somewhere in the box. This is the median. And the median, this is the middle number basically. So if we've got a list of data, the median is going to be the one that's smack dab in the middle. If there isn't a data point that's exactly in the middle, like if we have an even number of data points, then the median is the average of the 2 middlemost numbers. Okay, so that's the median. The ends of the whiskers are the minimum value and the maximum value. So you look at your data, you find the smallest point or smallest value. That's what goes over here. That forms the whisker on the left. And then the biggest one is the whisker on the right. Okay, and then the ends of the box, these are the first and third quartiles. So we call them Q1 and Q3. So quartile number 1, quartile number 3. And the way these work, Q1, this is the value such that 25% of the data is less than or equal to this. So that's by definition what the first quartile is. I, however, like to think about it in a different way because I think this is a little bit easier to remember. This is the median of the first half. So if we've got our data in a list, right? And we just go to the, well, let's just look at the first half. Then the median is that middle value for the top half. And so we find it the same way we find the median. We're just looking at concentrating at the top half of the data. So it's the middle value of the top half, or it's the average of the 2 middle values if they're an even number up there. All right, so that's what Q1 is. It's the first quartile. So then Q3 is the third quartile, and it means basically the same thing. This just says that 75% of the data is less than or equal to this value. And similarly, I actually think of it instead as the median of the second half of the data. So I do the same thing as before, which is I look at the bottom half of the data, and then I find its middle value, right? So if this is the bottom half of the data, I find the middle value there, the median, and that's Q3. So when we create our box and whisker plots, we basically mark these 5 values because they tell us a lot, right? We now know the total extreme values, the max and the min. So we know the total interval over which we're getting data values. We know the middle data value, which is the median. And then we know how this is broken down into quarters. So basically what you can do if you look at this graph, so think about what's going on when we've got a box and whisker plot is that this is somewhere on a, good old XY kind of axis or an X axis. And you can basically think of it as splitting it into 4 regions, right? We've got region number 1, number 2, number 3, and number 4, right? Or you can think of those as intervals of values. And basically what we've done is we've split it up such that 1/4 of the data are in interval number 1, and 1/4 of the data are in interval number 2, and 1/4 are in interval number 3, and 1/4 are in interval number 4. So we're just taking all of the data and we're breaking it into 4 chunks. But the box and whisker plot makes it so that it's a quick and easy way of seeing it instead of trying to sift through a big table of data. All right, so I think, was this Carolina that asked that? Is that kind of what you were looking for?
Yeah, it was just in reference to the homework question on the chapter 2 box plots assignment where it asks which interval has the most data. So I was just wondering what like the relevance of intervals to like the volume of data is on the box plot. So
Okay. So in this picture, if we were going to look at how much of the data is in each of these intervals, the amount of data that's in interval number 1 is exactly the same as the amount that's in number 2, as in number 3, as in number 4. These are all the same number of data points. But if we were to say like, okay, how many data points are in the interval between Q1 and Q3? Well, that would be half. Half of the data is going to be in there. So if we were told that maybe we've got data from 500 respondents, we go out and we ask 500 people their answers to a question, right? What's your age? We get our data. What I know is that half of them, 250 of them, would lie in the interval that's formed by the box. I'd know that 125 of them are in the interval between the box and the edge of the whisker. I know it's 125 because that's 1/4 of the 500 that we asked. So depending on what that question actually was asking you, and it was probably, like which of these intervals, and it may have said, between Q1 and Q3 or, whatever. That's how you can use this box and whisker plot to determine how many are in each of those, because 1/4 of your data is in each one of these. So take your number of data points, divide it by 4, and that's how many are in each one of these chunks. And so if you end up getting more than one of those, like if we combine chunks 3 and 4, that's 2/4 or 1/2. Or if we combine 1, 2, and 3, that's going to be 3/4 of the data, 75% of it. So without knowing specifically what they're asking in terms of which intervals, the whole idea of the box and whisker plot is that this is dividing it into 4 equal chunks. And even if we had, say, a smaller interval, like let me put some numbers here. So let's say that our minimum, we'll go ahead and say our min is 0 just to make life easy. Let's say that Q1 is at 10, the median is at 15, Q3 is at 25, and the max is at 30. All right, so let's just say that those are what our numbers were. And so what if I were to ask you how many data points or data values are between, let's say, 20 and 25? Now, obviously, I don't have a list to look at. If I had a list, I could literally go and count all the numbers. But here's what we know. If we look on this box and whisker plot and we look between 20 and 25. So here's 20 and here's 25, right? So I'm looking at how many data points do we have between 20 and 25. Now, I don't know exactly, but I can tell you for sure it's fewer than 25%. How do I know that it's fewer than 25%?
Because it's not taking up any more than 1/4.
Yeah, it's all within this interval between the median and the third quartile. So I know that any interval that's within this is going to be less than 25%. All right, so I know it's going to be less than 25%. I'll even put less than or equal, because it's possible that there are no data values between 15 and 20. Right? It's definitely possible. But I know for sure it's going to be less than or equal to 25%. Now you might go, well, that's exactly half of this interval, right? It's length 5 compared to length 10. So you might be tempted to cut that in half and say 12.5%. But the problem is we don't know how this data is distributed between 15 and 25. We could have almost all of them between 15 and 20, because the third quartile, it's just we're keeping track of when do we hit 75% of the data. We don't know how it's distributed within it. And that's one of the drawbacks of the box and whisker plot, is it doesn't specifically tell you where the data lies. It just tells you where fourths of the data are. Right. So you ask, if I was asked how much of the data is between 20 and 25, I know for sure it's less than 25%. But what if I was asked how much of the data is between, let's go 7 and 12? So if we go back and we look at our picture between 7 and 12, well, 7 is somewhere here and 12 is somewhere there. How much of the data is between 7 and 12? Can you give me an upper bound on it?
I mean, looking at it on the screen, it covers nothing. Like maybe just like the little beginning bit of the box, but there's not really like anything that it takes up. You know, it's like in the beginning.
Okay. So you're thinking it's pretty small?
Yeah.
Okay. Now, it most likely does have data in it, because there are data points in the box, right? And there are also data points on the whisker. Even though we don't draw a box, there are still data points out here. It's just, it's the smallest of them. It's the smallest fourth of the data points. So here's the thing. If you were to ask me this, how much of the data is between 7 and 12? The best I can say is that it's less than half. And I know it's less than half because it's all on the left of the median. Remember, up to the median is where half of the data is. So I don't have more than half in here, but I have no idea. I might actually have 40% of the data right in here. It could be that almost all of the data is right in here, and there are just a couple of small points out there. So again, because this goes over one of the quartiles, that makes it even worse in terms of my ability to estimate how much of it is in there. So at best I could say is that it's going to be under 50%. Right. In fact, I could for sure, I could even eliminate the or equal. I know it's going to be less than 50% because I don't include the minimum. But that's still not very good in terms of an estimate, right? How much of it is between 7 and 12? Well, less than half. And that's when you go, thanks a lot, Captain Obvious. But I can't give you a better guess without actually seeing the data. All right, so I'm starting to feel like I'm going around in circles. So I think I'm going to stop, but hopefully that helps a bit with the idea of what's going on with the box and whisker, at least in terms of the data distribution, at least at specific intervals.
So just to confirm, an interval is just any sort of number against that number line. It doesn't have to be specific to each quartile.
Correct. An interval is just from number A to number B.
Okay, got it.
Maybe
I wasn't
whatever.
sure if that was like a typo because I saw like numbers that were just a tiny bit off from what the like minimums and maximums were. So it could be anything against the number line, just a set of numbers.
Mm-hmm. Yep.
Cool. Okay, that makes a lot more sense now.
Yeah, an interval of numbers is just from any one point to any other point. And there are some special intervals, like with the box and whisker plot, right? When they correspond to things like the median and the max and all that. But no, in general, intervals can be anything you want.
Okay, got it. Yeah, I didn't know if that was a specific set of numbers and that I was reading it wrong, but makes a lot more sense now. Thank you.
Okay, you're welcome. All right, so any other questions on this one before I erase the picture and we go to something else? All right, hearing and seeing none, I'm going to erase that. Okay, so let's see, next thing I've got on my list here, I actually still have two on my list, but I'm gonna go ahead and talk about cumulative relative frequency real fast. So this is gonna look kind of similar. It may not, I'm sure not exactly the same as what was on your quiz. But let's say we're looking at, we go and we ask students, how many movies did you stream last week? And we get a whole bunch of different responses. Let me get to a nice number. So 10, 19, 21, let's throw on 4 more. Okay, so we asked 25 people. How many movies they streamed, right? All right, so this is the number of movies, and this is the responses. Actually, let me do it this way. Let me change that from a number to, we'll just write out the word. Okay, so this is the number of movies, and this is the number of people. So this is a frequency chart, right? A frequency diagram gives us a list of responses and how many people said it. So 6 of the 25 people didn't watch any movies, didn't stream any movies. 4 of them streamed 4, 2 of them streamed 3, and so on. Okay, so in terms of relative frequency, hopefully you remember how to find that, right? The relative frequency. It's just the number of respondents, or the number, how about we'll do this, the number in our category. Divided by the total number. Right, so the relative frequencies for these, if I were to make a third column, and we'll put over here the relative frequency. The first one's going to be 6 out of 25. The next one's going to be 9 out of 25, then 4 out of 25, then 2 out of 25, and 4 out of 25. All right, so these are your relative frequencies. So then cumulative, think about what that word means. Right, when something's cumulative, it adds up. Right, if we accumulate, we gather stuff. So that prefix means basically to add up. And so cumulative relative frequency, this is the sum of the relative frequencies. And I'm going to put here, it's a quote unquote running total. So let me add another column here for cumulative relative frequency. And so basically what we do is we just do a running count. So for 0 movies, we have 6 people. So that's 6 out of 25. When we go to 0 or 1, we now have 15 people. 6 plus 9 is 15 out of 25. Once we get to 2, we have to add up how many did 0, 1, or 2 movies. So that'd be 6 plus 9 plus 4, which is 19 25ths. The next one's going to be 21 25ths. And the last one's going to be 25 25ths. So cumulative, just keep adding. So if you look at the tops here, 6, 15, 19, 21, 25, that's what we get as we just add the next value. 6 plus 9 is 15, plus 4 is 19, plus 2 is 21, plus 4 is 25. So cumulative relative frequency, we just keep adding it up. All right, so I don't remember who asked about that one. but is that good? Feel all right about
Yeah,
that?
that makes a lot of sense. Thank you.
Okay, you're welcome, Ashton. All right, so any other questions on this? And really the idea behind cumulative is it helps you answer that question of like how many students watched 2 or fewer movies, right? Or what portion of students? And I go, oh, well, 19/25 watched 2 or fewer. So I'm keeping my running total. So it really helps you answer those kind of questions. All right, any other questions on this one before I clear and talk about lower class boundary? Good. Okay, so I think that this is where the lower class boundary thing is coming into play, but I'm not 100% sure without seeing the problem. But Ceremony, we'll see if this is good. If not, you just let me know. But let's say we've got a bunch of data and we are going to split it into histograms. So let's say that this is weight of dogs. All right, so we go out and we measure a bunch of weights of dogs. So we're going to get, let's say 15.7, 12.2, 20.6, 19.8, 18.4, 18.2, 13.6, and 14.9. Right. So he's got a whole bunch of weights. And what we want to do is we want to make a histogram that holds all of these. Cool. We've got 8. That's a good number. So what I want to do is I want to split this into histogram or into a bunch of categories, and I want, let's say, 4 categories. Right. So 4 categories / say intervals. So if we were just to look on the real number line, we'd see that the smallest one is 12.2. And the biggest one is 20.6. All right, now here's the thing about our intervals. So for our bars on the histogram, they have to extend beyond 12.2 and 20.6. So like the very first bar we see needs to actually be out here with its edge. And the 20, there has to be one that's slightly bigger than 20.6 so that all of our data is actually in the boxes. Okay. So the question is, what value do we give those? And here's the standard practice. This one would be 12.15. And this one would be 20.65. Now, I intentionally did not tell you how I got those numbers because I want to see if you guys can tell me how to get those numbers. How did I get those numbers? What do you think I did to get those?
Well, when you think about it, 12.15 is just half a percent lower than 12.2, and then 12.65 is just half a percent higher than 12.6.
Okay, and that's exactly the idea here, is that we're going to go a little bit bigger and we're going to go a little bit smaller. And the way we decide how much further to go out, the one thing I don't want you guys to catch from that, she said it's the percent. Percent actually doesn't really matter here because it's not always a half a percent, but it's always like half of the next decimal place. Right? So you think about all these numbers, they were all to tenths positions. So when I want to go out to make my next bar, I want to go to the next decimal spot, right? I want to go here, and I may need to go 5 of those. So I'm going to add 0.05 when I get bigger. So my plus 0.05. And I'm going to subtract 0.05 when I go smaller. So suppose that our numbers had instead been, with 2 decimal places. So we've got, we'll go with 15.70, but then let's say it was 12.21, 12.63, 81, 43, 29, 67, 93, or whatever. Okay, so now we'd have our lowest one is 12.21. Our biggest one is 20.63, which means I would have to change the numbers for my extremes, but it's the same idea. I want to go one more decimal place. So now it's the 3rd decimal place. And I want to either add or subtract that 5. So this is going to be 20.635. And this one would be 12.205. Because if I subtract 0.005 from this, I got to kick that 1 down. So it's always just the next decimal place. Go to the next decimal place and then either add or subtract 5. All right, so was that actually what we were asking about, Sermani?
Yeah, I think the question in the homework was a little bit different, but now that I look at what you did, if I would have done it like this, I probably would have gotten the correct answer. I think in the homework, if it was like 15.70, I think I just went 15.65.
Okay.
So this makes sense. Thank you.
Yeah, you're welcome. Anyway, so then the 4 categories or intervals, we would just take this length and divide it into 4. And then we would make our chart such that its height was how many of them are in between each of those. So, but it does all start with figuring out where to put the ends of those. All right, so cool for that. All right, well then I'm going to go ahead and stop sharing. And I'm going to slide back up to the whiteboard and we'll keep talking about data. So I'll be right back with you. All right. So last time we were talking about different kinds of ways of graphing and organizing information. And for example, we spent some time talking about the box plots and all that. Well, I want to show you another one. This is another one that's pretty common, especially when you have a large number of data points. And this is a good way to sort of get it organized while still having all of your numbers available, right? So you can still see all the numbers, because think about like a box plot, box and whisker plot. You lose data. You don't actually know the numbers, right? We didn't actually know the numbers in there. We knew the smallest one and we knew the biggest one and we knew medians in Q1 and Q3, but you don't actually have the data. Same thing happens with a histogram. You lose the actual data values. You know where they are, you know the intervals that they're in, right? That's what the little bars tell you, but you don't actually have the data anymore. So this one that I want to show you now actually keeps the data. It keeps the data, but it does organize it in sort of a smaller, more concise way. And these are called stem and leaf plots. All right, so a stem and leaf plot. You gotta love mathematicians, because we always describe things kind of how they look or how they behave, but we always try to relate them to something else. Like if you've ever had, if you take a math class with me, you're in a math class with me, but I mean like an algebra or something like that. I have all kinds of great phrases for random things, like with parabolas. I've got happy and sad parabolas. For those of you who know what parabolas are, that immediately means something to you. Oh, it's happy, it's a smile, it's sad, it's a frown, right? So I do that too, just ways to kind of describe that. Well, stem and leaf plots are kind of the same idea. With stem and leaf plots, basically what we're doing is we're taking numbers and we're breaking them into two pieces, a stem and a leaf. All right, so here's a generic number. Let's say we've got the number 314159. All right, so 314,159. Stems and leaves are designed this way or specified this way. We always trim off the last number. Okay, so this last number, that last number, this is the leaf. All the rest of it is the stem. So if you think about a leaf on a tree, you've got this nice long stem and then a leaf. Right? And so that's kind of how to picture this. This is the big stem that's coming out, and then here's the leaf. Now, the way that we use stem and leaf plots, let me give you an example. So I was thinking about what's a good example for this, and I started thinking about ages, because ages are good because they're two-digit numbers. We don't have to make really big stems. So I started thinking about, all right, I need a bunch of ages. So I just literally went through my head and thought about what are the ages of all of my nephews and nieces and brothers and cousins. Okay, so I'm going to give you a huge long list. These are all ages of people in my family. All right, so here is a data set. They are a bunch of ages, but it doesn't really matter, right? But I got 16 and 19, 22, 25, 26, 26, 32, 47, 51, 53, 56, 61, 64. Okay, so a whole bunch of ages. All right, now, since these are two-digit numbers, the stems are only length 1, right? Because the leaves are always the last number, and so the stems are what are before them. Okay, now imagine that this is like a tree. So I'm gonna draw a little tree here. So here's our tree, and we've got a stem, and we're gonna have a whole bunch of stems that are coming off of our tree. How many do I need? 1, 2, 3, 4, 5. So this tree needs to have 6. Okay, now these stems, they are stems that say 1, 2, 3, 4, 5, and 6. Because basically, if you look at the fronts of these numbers, they are 1, 2, 3, 4, 5, and 6. Now, with each one of these, there are some leaves. So for the 1, there are 2 leaves. There's a leaf up here and a leaf down there. And one of those leaves is a 6, and the other one is a 9. Okay, so the way to think about this is if we're going out the stem, we get a 1 followed by a 6. So there's 16. There's a 1 followed by a 9. Now, our 2 stem is going to have a bunch of leaves. It's actually going to have 4 different leaves. So let me draw 4 leaves coming off of that stem. And those leaves would have numbers in them 2, 5, 6, and 6. 2, 5, 6, and 6. So going out that stem, we get 22, 25, 26, 26. All right, so and so on and so forth. If we were to draw this little tree picture, and just so you know, the tree is not a stem and leaf plot. Okay, but this is why it gets that name. You can think of that stem as coming out, and then each of those last digits gets its own leaf off of that stem. All right, so here's how we actually do it. We're going to make like a T-chart. And on the left, this is going to hold our stem. So over here is going to be the stem value. And on the right, these are going to be the leaves. Unless you're from Toronto, I guess you can say Leafs if you want. That's a little hockey joke. Toronto Maple Leafs. They spell it wrong. They're crazy Canadians. All right, so here are our stems for this one. We've got stems of 1, 2, 3, 4, 5, and 6. Okay, so let me make my rows here in my chart. And then all I'm going to do under the leaves is I'm going to write the leaf values, and I'm going to go smallest to largest. So for the 1, there was a 6 and a 9. For the 2, there was a 2, a 5, a 6, and a 6. For the 3, there was only 1 in their 30s. In the 4s, there was just 1. In the 5s, we have 1, 3, and 6. And in the 6s, we have 1 and 4. So here is a stem and leaf plot for this set of data. All right, so why do we do this? Right, like, why do this chart instead of having this entire list? Well, really, it's less writing, to be perfectly honest. It may not seem like it, but think about this. All of these numbers that were in the 20s, I only had to count for that 20 one time, right? I wrote this 2 once for those 4 numbers. So it does actually make it nice and concise. And it helps if you go, okay, well, I'm really curious about which of these numbers are in the 20s. Boom, I can look just at this list and go, oh, there's a 22, a 25, 26, and 26. And that's especially useful if this data isn't ordered. Like I ordered it. I basically, as I was going through, I thought about their ages and went youngest to oldest. But if this was unorganized data, it'd be really hard to sift through and find all the 20s. Stem and leaf plot, boom, right there. What are the ages in the 40s? Oh, only 47. How many ages do we have in the 60s? Oh, we got 2 of them, 61 and 64. All right, so that's the idea behind a stem and leaf plot. They're actually pretty simple. All right, well, that's one more way that you can represent and show quantitative data. So just be familiar, that's another way. So let me talk just for a second about project 1. Remember, we've got that first project that's it's a couple of weeks away before being due. But one of the big things in this project is giving your information and showing it in charts and data and all that. So when you collect your data, and it's going to be quantitative, right? I asked for quantitative data. You're going to need to provide charts. So you're going to want to make a box and whisker plot. You're going to want to make a stem and leaf plot. Maybe want to is the wrong word. If you want a good score on your project, you're going to want to do those things, right? You're going to want to do a cumulative frequency table. You're going to want to do all those things. So the stuff that we've just talked about here in chapter 2 about displaying data, those are the kinds of charts and graphs you're going to need to include in project 1. Okay, so just realize that that's what we're talking about when you look at the description of what to do in project 1. All right, so now that we've sort of seen how to display this data, let's talk about some of the other numbers, some of the other characteristics that we care about with our numbers. So there are really 2 things that we look for when we're talking about a set of data. There are 2 important things that we talk about. One is the middle of the data, the center of the data. What's sort of the, where's the midline of this? Think about the box and whisker plot. We did that with the median, right? We always mark the median in the middle of our box because that showed us the center of the data. Okay, well, there are a couple other ways of getting centers of the data, so we need to talk about that. And then the other thing that we want to talk about is the spread of the data. How much does the data vary? Do we have all the numbers really close to each other? Like that example of ages of first-year college students, right? If you remember the numbers we had there's the 117, the 119, and a bunch of 18s. There's not a lot of spread there. Compare that to the ages I just put up here for the stem and leaf plot, right? That ranged from, what was the youngest one, 14 all the way up to 64 or whatever. Like, that's a huge spread. And so that's another thing that we want to talk about. So in order to do that, we have to define some new things. And so these are going to be measurements for the quote unquote center of the data. All right, so one of them is the median. And we talked about that with the box and whisker plots. I don't really feel like we need to get too much more into it. But remember, the median is the literally middle value. If you write all of the numbers in order, the middle one, the one that's smack dab in the middle, is your median, or the average of the middle two. All right, so that's one of the things that we often use for the center of our data. Another one that we use is the mean. And I talked about this when I made that mistake last time about using the mean for the center of the box instead of the median. But the mean is the average, right? So another way to think about that is average. So if you add up all of the values, all the data values, and you divide by the number of them, that gives you your mean. Okay, so those two, the mean, most people are really comfortable with. We find averages all the time. The median, hopefully you just get the feel, it's just, all right, it's the one smack dab in the middle. But there's another measurement that we use for the center of the data that is useful in other cases, and it's what we call the mode. All right. And unfortunately, yes, they all start with M. They're all M words. But you have median, mean, and mode. Now, what the mode is, so the median was the middle value. The mean is the average value. And the mode, this is the most common value. It's the one that comes up the most, right? It's the number that we see most frequently in our list. Okay, so we've got mean, we've got median, and we've got mode. All right, so let me give you some data here. And let's talk about the mean, median, and mode of this list. Okay, so like that example I showed you when we were talking about, I think it was the cumulative frequency just a bit ago up on the computer. Let's look at this. Let's say we ask people the number of movies they watched last week. Okay, so that's the question we go out and we ask, and we get a series of responses. So I'm going to make a chart just like I did before. So this is a frequency chart. Now I'm going to go with different numbers than I did there because I actually did the calculations with this set. So I want to use this specific set of values. All right, so we go out and we ask 25 people how many movies they watched. And this was their response. All right, so out of those 25, 5 people didn't watch any movies, 9 of them watched 1, 6 watched 2, 4 of them watched 3 movies, and 1 person watched 4 movies over the week. All right, so here's a set of data. Let's look at it and let's figure out the median, the mean, and the mode. Now, I want to show you how to do this with a chart like this instead of just a list. because it's much more frequently the case that we get a table like this with responses and their frequencies than the actual list. Okay, now I'm going to start with mode because the mode is easiest. Basically, we just look at this chart and we go, okay, of those responses, 0, 1, 2, 3, and 4, which one was responded most frequently? So in the chat box or yell it out. How many movies is the mode? All right, so I see 4, 1. I see a bunch of ones coming out here. Okay, so the mode is 1. Because it's got the largest number of responses. Okay, so it's really easy to tell what the mode is. You just look and see which one has the most responses. So notice what I'm saying here is got the largest number of responses, not the largest number of movies. And I don't remember who that was that threw a 4 in the chat box, but maybe that was the interpretation there. But this is of the 25 people, what answer did they most often give? Well, they most often gave the answer 1. All right, so there's the mode. Cool, pretty easy. All right, now let's talk about median. You know how to deal with median if you just have a list, right? You find the middle number and you call it good. Well, I don't have a list. I've just got this frequency table, but we're actually going to think about it the same way. All right, suppose that I were to make a list of this. I would have, well, 5 zeros. So 1, 2, 3, 4, 5. I would have 9 ones. 1, 2, 3, 4, 5, 6, 7, 8, 9. I would have 6 twos. 1, 2, 3, 4, 5, 6, followed by 4 threes. 2, 3, 4, and a 4. All right, so I got to find the middle value. Well, since there are 25 respondents, halfway is 12. So let's just count that by 12. So if I go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, that's number 12. That's number 12 on my list. If I count backwards 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, that would be this one. So I need the value that's exactly dead center in the middle, which is 1. So it turns out that for this one, the median is also equal to 1. But you don't want to have to write out this list every time. Because what if, kind of like that one on the quiz, remember the one on the quiz about the fish? We had 300 blanks. Can you imagine if I gave you a list of 300 blanks and said, find the median? Ugh, nobody wants any part of that. So how can we be smarter about this? Anybody see a way that we could be smarter when we've got a table?
Are we talking about for the middle value, right?
Yep, for the median.
Yeah, to take the full amount and divide it by 2, and then take that amount and go that far down the line. Like, so for 300, you'd go 150 in, I think, right?
Yep, exactly. Yeah, that's how we're going to be smart about that. And I think that was you, Elisha, right?
Yes.
Cool. So thanks. That's exactly what we're going to do. So we have 25 respondents. So let's think about cutting that in half would be 12 and a half. Well, that half is a bit of an issue, right? But since it's an odd number of respondents, we know there will be a middle value. So here's what we're going to do. We divide it by 2, and we get 12 and a half. Round up to 13. The 13th one is our middle, right? So here's what I did. I took n divided by 2, and then round up. If it's an even number, then you're good. You know what how many there are in top and in bottom. But if it's odd, you round up. So I'm going to put round up if needed. Okay, so I really need to know, where is the 13th number? Well, this kind of comes back to that idea of cumulative frequency. Remember the cumulative relative frequency? We kind of keep adding up. Well, let's do the same thing, but just with the number of responses. So I need to find the 13th one. Well, there are going to be 5 that are 0. So I need to go 8 more spaces. Well, 8 more spaces brings me somewhere in the group of ones. So just by looking at this, I was able to figure out that my middle number, the 13th one, is somewhere in the ones. So that's why my median is 1. Now, it turns out in this case, the median and the mode are the same. Coincidence. Coincidence. It's not usually the case that that happens. But in this data set, yeah, all right, median and mode are the same. All right, so lastly, let's find the mean. Now, just like with the median, we can take this entire list and find the mean. Right? We're going to add them all up, take whatever that number is, and then divide by the total number of answers, of numbers, which was 25. But I don't want to make the entire list. I want to kind of speed this up a little bit. So here's how I'm going to find the mean. All right, well, I need to add all these numbers. So I'm going to add 0 plus 0 plus 0 plus 0 plus 0. So I'm adding that same number over and over and over again. And remember, the fast way to do that is multiply. So we're just going to multiply. I'm going to take 0 and I'm going to multiply it by 5 because there are 5 zeros. Okay, then I'm going to add a whole bunch of ones. Well, so I'm going to do 1 plus 1 plus 1 plus 1 plus a whole bunch of times. So that's, again, multiplication. How many ones are on that list?
9.
9. And you can either count it out or recognize, oh, wait, that was the respondents there. So I'm going to have 9 times 1. And then I need to add up all my 2s. Well, there are 6 of those. So 6 times 2. And then all my 3s. There are 4 of those. And then my 4s. Well, there's only 1 of those. And then I'm going to divide that whole thing by 25. So notice what the fast way is of doing this. I have 5 times 0. That's these two numbers being multiplied together. 9 times 1. Those two numbers. 2 times 6. 3 times 4. 4 times 1. Okay, so the fast way, if you want to find a mean when you're given a frequency table like this, is just multiply the values times how many responses, and then add all those up. All right, so if you add all these up, I forget what you get. You get 37 25ths. So adding all those up gets you 37. We're still dividing by 25, which is 1.48. So our mean is 1.48. So mean, median, mode, they all tell you something different, but they're all a measurement of sort of the center of the data, right? So the way to interpret this is the number of movies most frequently watched was 1. Half of the people watched at least one movie, half of them watched no more than one movie. Right? That's the way to think of that median. So it cuts it in half. But on average, they watched 1.48. And again, nobody actually watched 1.48 movies. Well, maybe they did. Maybe they fell asleep in the middle and they didn't catch the second half. But if we're just going to go with a whole number, yeah, nobody actually just watched 1.48 movies, but on average, the mean value is there. All right, so how do we feel about these three measures of center? Feeling okay? Thumbs up? Any questions on them? All right, cool. I'm seeing lots of thumbs up. That's what I like. All right, so let's move to this idea of spread of the data. So that's going to be the next question. What about the spread in the data? Because we want to be able to describe that. We want to talk about, well, are all of our numbers really close to that mean, that median? Are they really spread out far? Right? We need a number that describes that. So what we're going to use is what's called standard deviation. Okay, and I will talk about what standard deviation is and how we get there, but we need to know a couple of things before we get to standard deviation. However, I am going to show you the symbols that we use. Right? If we're talking about a sample, we use the letter S. That makes sense, right? Sample, standard deviation. Sometimes you'll see a little subscript on it. You'll see a little sub X, right? But I'm going to be lazy. I'm just going to use S, right? So if you see S, that means it's the standard deviation of the sample. So take like this example with the movies, right? We take these numbers, we plug them in to the formula for standard deviation, we get a number. That's going to be an S because that's the standard deviation of the sample. Okay, if we're talking about the population standard deviation, we use the letter sigma, which is sort of like a little squished 6. Okay, but this is the Greek letter sigma. It's the lowercase. It's their equivalent of S. So it's the Greek equivalent. So there's a difference if we're talking about population standard deviation or population or sample standard deviation. So we use different letters to describe them. And I want to back up real fast because I just realized I didn't tell you that we do the same thing with mean. There's a difference between sample mean and a standard and the population mean. And we use different symbols for those two as well. So let me just backtrack real quick and show you that. Just the symbols for them. Okay, so for sample mean, we use X with a bar across the top. Actually, I think I may have mentioned this before, but what we say, like if you want to describe that symbol, we literally call it X bar, because sure. All right, so that's our sample mean. Our population mean, we use this guy. It looks like a little curvy U. This is also a Greek letter. It's the Greek letter mu. It's their equivalent of M. You'll notice, I don't know if you've even noticed this coming through math, we use a lot of Greek symbols. It's kind of an homage to the Greeks for all the math they did back in the day. You see it a lot in like geometry and trig and stuff. Anyway, just so you know, if you see those symbols, we're talking about sample mean versus population mean. Just like we've got different symbols for sample standard deviation and population standard deviation. But it's important that we know that there's a difference, right? Like, look at this list of the 25 people that we asked and how many movies they watched. We don't know that this mean of 1.48 is actually the population mean. Like, it could be really far off depending upon how we chose our sample. So that's why it's really important for us to recognize, oh, that's a sample mean. A population mean, who knows? But hopefully our sampling is such that it's done it properly so that our sample mean is close to the population. And as we go further on this quarter, we'll definitely talk about how do we know how good our sample is versus the population and all that. But for right now, just realize there's a difference. Okay, so let's come back to standard deviation. These are the symbols we use, but how do we actually calculate it? How do we get the standard deviation? Well, to get the standard deviation, I need to tell you about, I don't need to tell you about a couple of things. Let me just show you the formula for this. Okay, so if you want to calculate your sample standard deviation, you got S here, it's the square root of a fraction. The fraction has in its top the sum of x minus x bar squared. And on its bottom, we have n minus 1. So that's its formula. I'll explain what that formula, what everything is in a second. And then for the population standard deviation, it looks very similar. Except this time it's a sum of x minus mu squared divided by capital N. And this is when you go, oh man, I want to go back to means and medians and modes. Ugh, gross. Okay, well, let me just sort of break these down so you can see what all the different pieces are. All right, so first of all, N. N is the sample size. All right, so it's the actual number in our sample. So thinking about this example where we have the 25 respondents, little n is 25. Okay, so that's what n is. All right, so we're going to divide by one less than our samples. Okay, so then let's go look at the top. So first of all, we've got a sigma. You guys remember what that means? What is this capital sigma, this pointy E? What does that tell you to do? Anyone remember?
Population standard deviation, or is that what we're talking about right now?
I'm talking about this big guy, not the little guy. And this is the weird thing. This is a lowercase sigma, and this is a capital sigma. You know, kind of like we have lowercase and capital letters. So do the Greeks. So we've got a sigma inside of our sigma. So I'm talking about the capital sigma. This is something you hopefully have seen prior to this class in algebra or something. And Carolina just put in the chat box exactly what it is. It's a sum. Okay, anytime you see this capital sigma, this means sum. So we're going to add up a bunch of things. That's what that sigma means. We're going to add up a bunch of things. Now, what we're going to add up is a bunch of squares of differences. And notice here what we got is x and x bar. So x bar, I just told you, was our sample mean. So when we look at x minus x bar, that's how different our number is from the sample mean. All right. So think back to this example with the movie stuff. Suppose we look at one of the people that was watched 2 movies last week. Okay, so 2 is not the mean. So the difference between 2 and the mean is 0.52. And then we take that 0.52 and square it. So we would do that for all of the people that watched 2 movies. For the 3 movie people, we take 3 minus 1.48, get 1.52. Square that, do that for each of those people, and so on and so forth. So we're taking the squares of those differences, adding them all up, that's what that means, and then dividing by, in this case, 1 less than the sample size. And then we take its square root. Yeah. Okay, well, that's how it's done for the sample standard deviation. For the population standard deviation, you'll notice it looks very similar. It's still a square root. There's still a sum on top, but now instead of x minus x bar, it's x minus mu. We're still looking at how far are the values off of the mean. It's just now we're using the population mean instead of the sample mean, because we're talking about the whole population. And then we divide by this big N. And what big N is, this is the number in the population. So it's the entire population. So if we were looking at, let's say in our little study here, we're looking at numbers of movies. We were curious about the numbers of movies watched by all college students in the United States. Then big N would be the total number of college students in the United States, as opposed to the 25 that we asked as little n. Okay, so that's what all these different things mean. And this is how we actually calculate the standard deviation. So I will show you how we calculate the standard deviation with this chart. But then I'm going to show you how you're going to really calculate standard deviation. All right, so we need to know all these different numbers. And so here's what I'm going to do. I'm actually going to extend my chart here a little bit. So that it has what's useful for standard deviation. So it's great knowing the number of movies and all that, but I also want to know x minus x bar. I need to know that number so that I can calculate my standard deviation. Okay, so x bar, that was the mean, and we already calculated that. Right? Remember x bar, let me rewrite it. It was 1.48. And x, that's this column. That's the response, that's the actual number of movies that people watched. I want to see how far are those numbers away from the average. Okay, so I'm going to take 0 minus 1.48, which is negative 1.48. I'm going to take 1 minus 1.48, which is negative 0.48. And I'm going to take 2 minus 1.48, which is 0.52. 3 minus 1.48 is 1.52. And 4 minus 1.48 is 2.52. Okay, so I just calculated that number, x minus x bar, right here. Calculated that for each of these x's. Now, what I'm going to need to do is square them. So I'm going to take negative 1.48 and square it. I'm going to take negative 0.48, square it. Positive 0.52, square it, so on. And then I need to add them all up. All right, well, we're going to add them up in a fast way again. But this is what that standard deviation is going to look like. It's going to be 5 times negative 1.48 squared plus 9 times negative 0.48 squared plus 6 times 0.52 squared. I'm running out of space. Uh-oh. Plus 4 times 1.52 squared plus 1 times 2.52 squared. And I'm going to divide that all by 24. So I'm, again, just doing this the fast way. Since I'm adding negative 1.48 squared 5 times, I'm multiplying by 5. Since there are 9 of them that are going to be minus 0.48 squared, I have 9 times that, and so on. So I add all those up, I divide by 24, and I get 1.122, roughly. Okay. So this is the standard deviation for the sample. Now I know it means absolutely nothing to you. You see that number and you go, okay. We'll talk about the relevance of it in a second. But let me explain why it's actually giving you a measure of spread. So think about this x minus x bar. That's how far our data point is from the mean, right? It's just literally how far away it is. When I square it, it makes it so it's always positive. So I don't have to worry about which side I'm on. When I add all those up, it's basically giving me the total variation off of these things. And then I take a square root to cancel off the square. Now, why I divide by big N or N minus 1 is to make it an average. So it's basically the average square of that difference with its square root. So that's why it's giving me a measure of spread. If all of my numbers are close to the mean, x minus x bar is going to be small. So this is going to end up being a very small number. So a small standard deviation means that all of your data is close to the mean. If our data points get really far away from the mean, these things get big. If I add up a lot of big numbers, I get a big number. All right, so really the way to think about this, and what this tells you, I think I'm done with our chart of all the data, so let me just erase this. So small standard deviation means little spread. And big standard deviation equals large amount of spread. All right, so this is how we're going to measure it. We're going to calculate this thing called the standard deviation, and that's basically going to tell us how far or how much our data is spread. All right, so I think probably at this point, many of you are like, oh shit, this is going to suck. Calculating standard deviations, I don't want to do that. And you're right, you don't want to do that. You don't want to do it by hand. And that's why we're going to use technology. All right, so this is where your calculator is going to come in handy, or whatever computer program you're using to do your statistics. All right, so let me just show you on my calculator how this plays out. So I have a TI-89. You guys might have something different, but they all kind of have something like this. And under the TI-89, with TI-89, I've got a command, a little window that's called stats. You might have one that says data, list, something like that. But there's a place for you to actually put in your data. Now, this is where if you've got either TI-83, TI-83 plus, an 84 or an 84 plus, look at the book. The book explains the steps for how to put this stuff in. It's all throughout the book, so it's not like I can tell you, oh, go to this page specifically for whatever, but you can find it in there. If you don't have one of those calculators, you can always hit me up. I can try to explain. If you're using a spreadsheet like Excel or Google Docs or something, they also have, like it's really easy to put data into a spreadsheet, but they also have commands to do the statistics, right? So you want to use your technology to do this. Now, what you're going to be calculating, if you want to find standard deviation, median, mean, all that sort of stuff, you're going to be doing what are called one variable statistics. Because you may remember variables, right? Variables are the thing, the number that we're getting answers to, right? And in this case, we only have one variable. How many movies did you watch? Right? There aren't multiple. So that's why it's one variable statistics. On my calculator, and I think on the rest of the TI 80 versions, it will say one var stats for one variable statistics. All right. So I'm sure you can't see it on mine. Well, maybe you can. Let's see if we can get it to focus up there. So if you look at that little list of things, and it's so out of focus, it doesn't matter. Well, that one that's black that's highlighted says one var stats. Below it, there's two var stats. Then it says regression, probability, like it's got all kinds of other stuff it does. But what you want are one variable statistics. Now, depending upon how you have your statistics, you can do this in different ways. But if you do that and you run one variable stats, let me just tell you what my calculator gave me. It gave me the sample mean. So it spit out the 1.48. It also tells me the total value of all of the responses, gives me the sum of those squares for whatever reason. It gives me a standard deviation for my sample. So it gives me an S. It gives me a sigma. So it gives me the standard deviation for my population. It gives me the number of elements in my sample. It gives me the minimum, the first quartile, the median, the third quartile, and the max. So if I wanted to make a box and whisker plot, it just spits out that information. And then it also gives me the sum of the squares of the differences between X and the mean. So remember this thing up here, it gives me that total as well. So there's a lot of information that it gives me fast and free. I just have to make sure that I put my data in properly. So I can't stress enough, whatever technology you have, now is when you want to learn, how do I put my data in and how do I get useful numbers? All right, and this isn't something that I can necessarily do in class because we all have different technologies. But if you are having issues with that, come find me during an office hour. Send me a message so we can get together another time so we can work it out, because I want to make sure you know how to use your technology to get these numbers, because you don't want to do this stuff by hand. You do not want to do that. They only get worse from here. If you think this is bad, oh, just wait. Just wait until you see some of the formulas for other things. Okay, so your homework this weekend, in addition to doing homeworks and all that, is get to know your technology. Get to know your technology so that you can get these useful numbers from it. All right, now, this is how you're really going to do it. You're not going to use the formula. But what does that standard deviation actually mean? Like, who cares? Who cares? What does this 1.122 tell me? Well, it turns out that there are a couple of rules named after, well, one's named after a Russian mathematician who fiddled around with this stuff. But we definitely have some rules that tell us about how data is distributed. Okay, so this first one is called Chebyshev's rule. Yeah, it's a fun word to say. This guy's name. So it's Chebysheshev. So Chebyshev. So this is Chebyshev's rule. Now, what this says, and this is absolute truth, regardless of how the data is distributed. So no matter what this looks like with the data, it's spread out, close, like whatever. But regardless of how the data is distributed, we know at least 75% is within 2 standard deviations of the mean. So think about this guy right here, the 1.122. If you were to go 2 standard deviations, that's 2.244. You know that at least 3/4 of the data is going to be within 2.244 of the mean. And you know how I said, oh, I think I'm done with the chart, don't need any more? Yeah, I wanted to look at the chart. But let's just look at this for a second. So we knew the mean was 1.48. Right, with our example, it was 1.48. If we look at 2 standard deviations, that's 2.244. So I know 75%, at least 75% of the data is between, well, on the high side, I'm going to have 3.724. And on the low side, I'm going to have negative 0.766436. Oh my goodness. No, hold on. That's completely wrong. 2244 minus 1.48. 467. That's better. Okay, so at least 75% of the data is going to be between negative 0.764. Well, we know it's not going to be negative because you don't watch a negative number of movies. But if you were to look at all our numbers, the values that are between these two numbers are 0, 1, 2, and 3. And if you go back and you look at that, at least 75% of them are in there. It's more than that. But we know at least 75% is going to be between within 2 standard deviations of the mean. All right, well, even stronger is if we were to go 3 standard deviations, we know that at least 89% is within 3 standard deviations of the mean. And if you want to catch almost all of it, I mean, 89% is already a ton, but at least 95% is within 4.5. So you're starting to see why the standard deviation matters. If we know what that number is, regardless of how the data is distributed, we have a decent idea of how much of our data is within a certain distance of the mean. You can also see why a smaller standard deviation means your numbers are closer together, right? If your standard deviation gets small, going out 2 standard deviations isn't very much. And so you'll catch 75% of that data in a really small interval around the mean, as opposed to a big standard deviation, which makes it spread out. Okay, well, this is Chebyshev's rule, which is true for any kind of data. But there's an even better rule for if our data is good data, nice data. I'll say nice, good is the wrong word, but nice. Okay, so check this out. If your data, well, we call this the empirical rule. All right, and what this says is that if your data is, I'm going to put here in quote, bell-shaped, and symmetric. So if we're in a situation where our data is bell-shaped and symmetric, so symmetric means it looks the same on either side, so it's not skewed, we don't have weird peaks in weird places. And it's bell-shaped, meaning if you were to actually draw a graph of, let's say, do like a bar chart or a histogram or something, what it would look like is something like this. Okay, so kind of bell-shaped. We'll talk more about actual bell-shaped and what that means. There's a distribution called the normal distribution. We use that one a lot, which means we get to use the empirical rule. But if we've got the empirical rule, then what we know is that 68% of the data is within 1 standard deviation. So if you only go 1 standard deviation on each side, you catch 68% of the data, roughly. If you go 2 standard deviations, this is awesome, you get about 95%. And if you were to go a whopping 3 standard deviations, you catch more than 99%. So you notice that these numbers are a little bit bigger than what we see with Chebyshev's rule, but that's because this kind of distribution is nice. Like I said, it's nice data. But in this situation, man, standard deviations, you don't have to go very far to catch almost everything. Like, look at it, 2 standard deviations and you already have 95% of the data. Wow, that's almost everything. So this is why we care about standard deviation, because it really does give us a measure of spread, lets us know how good our data is. And we're going to use it later to determine, if we get a response to some question, we go, ooh, is that a normal response? Is that a weird response? Is this something that is out of the ordinary? Standard deviation is going to let us know. All right. Okay, so there's a little bit about standard deviation. I see on the clock I got about 10 more minutes, but I'm going to stop because this is a really good stopping point. We've now talked about data a lot in terms of how we represent it, how we show it, and everything. And we are now done with chapter 2. All right. So if you look at our schedule, we're one chapter behind. Again, don't worry, we got plenty of time to catch up. But just so you know, we're done with chapter 2. We're going to be heading into chapter 3. I need to check and see if chapter 3 homework is due Tuesday night. If it is, I'm going to extend it to the following week because we haven't talked about it yet. I just don't know off the top of my head which ones are due on Thursday or Tuesday. But I do want to remind you, Tuesday night at midnight, your first homework set is due. And I believe it's chapters 1 and 2, I think. I'll make sure that it does not include chapter 3. We still have time on Tuesday to ask questions and chat about this stuff. So I'll be more than happy to do that. I'll also get the quizzes graded. You'll see my comments on them and your scores pop up through Canvas. That should happen, well, for sure by Tuesday. I don't know exactly when, but just be aware that that will be coming as well. All right, so with that, I'm going to go ahead and stop our recording and wish you guys a wonderful weekend.
Have a good